Okay, good morning. So today I want to start a new sort of a topic and phase in our course, which is with the material we already have, we can definitely start understanding some research problems. Particularly, I'm going to show you some of those that I've been involved, which actually combine and put research problems that combine mathematical modeling, numerical modeling, and scientific computing, which is very much sort of the spirit in the work I do. Now, not always we have all components, but right? So, and also for what is the motivation for this? So let me put it here, which I'll do it. Mathematical modeling, which is choosing PDE, or which is a little bit the spirit of what I'm going to talk today, obtaining reduced models, which is reduced PDEs. Some of you who did the course with me, either in fluids or PDEs and applications, have seen this, so I'll repeat it a little bit. Numerical modeling, which is related to this also, which has to do with PDE plus numerical method. We've seen sometimes we can go for a differential equation, or from the differential equation, because we want to do something numerically, we go, oh, let's do an integral equation, right? So that's choosing the mathematical object we want to study. And here is basically the scientific computing comes in several flavors in my research. That can be to illustrate the theory. Many times the theoretical aspects are very complicated, so we can't prove theorems, but we can indicate something through an asymptotic analysis, a formal asymptotic analysis, and then we want to illustrate the theory. The Krasny problem I showed you is an example of that, because Moore's results were very complicated mathematically, but he couldn't prove a theorem, and Krasny provided evidence, numerical evidence of the results. So illustrated the theory. Sometimes this also is to provide intuition into, let me say it like this, theory. This is many times the aspect of the scientific computing. And other times also, let me put it like this, all are related to this, is also to explore physical properties, say unknown. And this is one thing that, for example, in my recent research with the bouncing droplet that some of you have seen, is very much in this direction. So basically doing computational physics, but with having a mathematical background. So this is the spirit of this. Research problems in applied math that combine these ingredients that vary. How much of this ingredient varies from problem to problem. So the bouncing droplet, for example, has all these three ingredients. A math modeling, which we actually did the first equations for a droplet with a wave. A numerical method, because we use the Dirichlet to Neumann map, which I mentioned to you here. These are things that this month I might be talking here and there. But I'm going to start with the wave problem over topography. And scientific computing, which is to illustrate the formal theory, meaning formal means no theorems, because it's too complicated, so you do asymptotic, formal asymptotics, whatever. Providing intuition, that this has happened too, where through computations, I convince some more theoretical colleagues from specialists in probability theory and so on to work together. Say, hey, I basically know the result, but theoretically I don't know how to get the result. I have some ideas of intermediate steps, and this was something that worked very well, and so on. Okay? So I'm going to start. So to exercise these 3 points, okay? Say one, let me put one, math modeling, 2, and 3. And I'm going to start with math modeling, which is something, but I want to register on the video, but something that most of you, not all of you, have seen either in the PDEs course a little bit, or in the fluids course a little bit. And here I'll show it a little bit, but even because, you know, this is not the PDEs or the fluids course, but so that I can then motivate why I'm doing this, also thinking of the theme of this course. And that's actually also what I did, thinking of obtaining a simplified model, okay, a reduced model, so that I could do better numerical methods in a good way, and so on and so, and actually discover things as I did, then convincing my probabilistic friends, Jean-Pierre Foucault and Jocelyn Garnier, in a very nice problem. Those are the 2 luckiest problems in my life. They're really like lottery tickets. Really like, I feel very for lottery tickets. One that I maybe never mentioned to you was just time reversal of waves. I'll tell you a little bit, came from acoustics and with water waves. And the other one is this bouncing droplet problem that some of you, or most of you, have seen me talking, okay? So let me tell you how I prepared things, right, to do the time reversal problem, which I'll tell you a little bit about it, and that I had to prepare the terrain, the PDEs and so on, and start doing some numerical simulations to then convince my more theoretical friends to jump into the boat and collaborate, okay? So this is the story today. So I'm going to start with a sort of a quick review, not quite a review for somebody, but a quick story that starts from PDEs, the modeling, and going to, to the reduced modeling. Okay, so actually let me write here. So I'm going to start with a paper of mine, a solo paper of mine, which is this paper. I will send it to you. So this is a paper, Science Applied Math 2003. And the problem is like this. Let me show you first the figure. So the problem is like this. This problem is actually inspired by this problem. Say, let me put this paper inspired by the work of Papanikolaou and collaborators in acoustic waves, which is this problem here that we saw already. Acoustic waves in the crust of the Earth. Okay, so this problem I already showed to you. It's was a hyperbolic system and so on. Then I wanted to do the water wave problem. Which is, the analogy would be this. So waves, excuse me, water waves over steps. Okay, this is like the bottom of a channel, right? So this is a simplified version, like a little Lego type topography, but it's like more, you don't quite see this in the ocean. You could do this in the ocean if you say, oh, let me not see the fine scales at the bottom, let me just do an approximation. Like sometimes this is done, actually in atmospheric flows, but still, let's think of this first as a warm-up mathematical problem, okay? So we have this piecewise. Why this? Because this has an analogy with this. The wave speed is constant, piecewise constant at each of these steps, and similar to this. So the shallow water equations here, which I showed you, the shallow water system, is similar to this one. But then now it's just a story. I'm not showing you this. Sometimes in the PDEs course we see a little bit of this, is that the shallow water system, when we think that this is lambda, this is h. So when h over lambda is small, and in the limit as this goes to 0, this system of equations, the shallow water equation, hyperbolic equation, is not valid, okay? So there was a paper in my PhD time that I found and so on. So I wanted to get a system, so here starts the story of this paper. I wanted to get a system of differential equations that looked like this one, the acoustic one, a little more general because it has, for example, dispersion and so on. This is hyperbolic. And that was valid, at least formally valid, for a topography like this, which is rapidly varying with respect to the wavelength. Okay, so this, if the wave is order 1, this is actually epsilon. It's basically a rapidly varying coefficient. Why this? Because there was some theory by Papanicolaou and collaborators for the acoustic wave that dealt mathematically well with the sort of averaging, the average feeling that this wave has from the bottom. And I wanted to do the same. I wanted to import, understand the theory. This actually started from my PhD thesis, but there were many things we discovered actually that there were many things yet to be done, right? When Papanicolaou proposed the problem, it looked like it was just an analogy, but it was not so straightforward. And there was an equation that was not the shallow water equation for this rapidly varying system. I'm not going to show you here, just a comment, was not valid. So what did I do? So I ended up doing something theoretically that later on I learned how to do it numerically, and later on there was this almost like gift that came through the internet, which is the Schwarz-Christoffel toolbox by Toby Driscoll, which was a student of Trefethen. So he used things of Trefethen to do conformal mapping numerically. I want at some point here in the class to show you that, give an indication how to use it, because it's free, it's beautiful, and when you become doctors and you have your students and so on, it's a nice thing to use in the complex variables course. Okay, so I'll show you how to use it. And that was the ingredient for me to be able to simplify the equations, the conformal mapping, get a simplified system of equations, and do proper numerics, which is the theme of this course. Okay, so basically, I'm going to show you how we get from here to here and to here. Okay, and using then articles of my research. Okay, so the idea is like this. I'm not going to give all the details of the conformal map, so I'm going to then do, I started actually with a weakly nonlinear. I was looking through my notes, and actually I wasn't clear. Did I ever show to you here in this course? I don't think so. Because I showed it in the fluids course, and most of you did a fluids course, but not everybody, and also in the video. I showed a little bit of this in the PDEs course, which is also in the video of the previous course, but not in this one. The water waves equations. For example, I think you have never seen it, right? Okay, so I'm going to show you the water waves equation. So let me write it. So here's the problem. So the problem is like this. Let me start with a straight with the topography like this. So I have scales, lambda, A, H0, and little lb of the bottom, okay? And this is what we call nonlinear potential flow. And we solve the problem like this. Let me go back because here I have the, and like this, so I'm going to get confused with so many things in my hand. Okay. So we have this equation here. Let me write it and then I'll explain, okay? Just give me a second, please. But you see how complicated the problem is. Okay, so here's how the story starts. This problem is difficult, right? It's a free boundary problem. Okay, it's a free boundary problem, and I have dimensionalized it. I think I have everything here. So look at this. Oh, and I forgot to say, so eta. So this is the wave elevation. Eta. And phi, let me put here, is the potential, which is the gradient of phi. That's why it's potential theory. So this problem is it's a very difficult equation, very complicated. Because, so here is my axis, x and y. Okay, so here is y equal to the elevation. Here is y, this is the bottom. This is the bottom. And what do I have? I have Laplace's equation scaled. It's a scaled Laplace equation, scaled for long waves, y for long waves, because I'm putting this smaller than small. This small, and this is small. So this means weak nonlinearity. Why? Because the alpha multiplies all the nonlinear terms. Weak dispersion, which is these betas, or this indicates if we have long waves or shallow channel. Why? Because if this is small with respect to that, it means the wave is long or the channel is shallow. Okay? And why is it called weak dispersion? Because the beta is small. If we do a Fourier analysis of the linear equations, and we look at the Fourier relation, you know what dispersion means, right? The Fourier modes have different speeds and so on. So it's in that sense. So I'm not going to do all the details because or else I start doing the PDEs and applications course. I just want to do enough so that we understand the numerics and the math modeling. And ask me questions if I go too fast, right? And I'll say, oh, don't worry about this, or no, sorry, I have to explain this a little more. Okay, so stop me. So these are, so the original equations, the physical equations, are very similar to this, but it has physical parameters. This is the dimensionless equation. What is dimensionless equation? Some of you, or most of you have seen is that you change variables, you scale things so that you have dimensionless variables. It doesn't have dimension anymore. But parameters appears that helps us control which regime we are. So alpha is the nonlinearity parameter. And this is kind of obvious if you look here. Multiplies all the nonlinear terms. And it also shows us that the free boundary problem is another source of nonlinearity. Why free boundary problem? Why? Because these two equations here, which are the two evolution parts, they are imposed at a boundary which I don't know what's going to be in the next instant of time. That's why it's a free boundary. It's part of the problem to solve where the boundary is, because it's a wave problem, right? This is the free surface, this is the topography, and this is the water. Okay, that's why it's a free boundary problem. But if I linearize the problem, it becomes, I can impose my boundary conditions at the undisturbed free surface level. Okay? So the linear problem, I remove the nonlinear terms, and I also get as an extra prize the fact that I can impose my conditions at the undisturbed level. Why? Physically speaking, because the linear problem, we think of the waves of an infinitesimal disturbance. Because the amplitude is small, so you can put the condition at the undisturbed level. That makes life simpler, not so simple, a little simpler, mathematically speaking, and numerically speaking. Okay, but let's start with a nonlinear problem, and then what do we say? The weakly nonlinear, weakly dispersive, because these parameters are small. They're not zero, but they're small. So weak nonlinearity, weak dispersion, and this parameter here tells me, which is the regime I'm interested, and the shallow water equations were not valid, which is I want to study the rapidly varying regime where the topography varies very fast with respect to the wavelength. And I can see, and I want to study what is the effective, what is the interaction of the wave with the topography. And there are many interesting things. I'm going to speak about this, some of it today. And also the time reversal is another one. When this interaction, if you wait long enough. Now here's another challenge. If the mathematical theory tells us that something important will reveal itself if I'm able to wait long enough, okay, because it's an asymptotic theory, I have to have a numerical method that's what? Stable and accurate for a long time interval, right? That's correct. Stable and accurate, and able to resolve the microstructure. Okay, so in this wave problem, usually this, for the water waves, if this is a tsunami, okay, and that's actually when I give talks. Unfortunately, we don't have tsunamis in Brazil, but that is a problem, right? It's a large disturbance. It's really, when I give talks, in particular outside of Brazil, I talk about tsunamis, which are very important. This is a problem for you to understand tsunamis over in the coastal region, how it will interact with the topography. And a tsunami is like 100 kilometers long when it starts. So the microstructure is 100 meters, maybe even 1 kilometer can be a microstructure, because it's all relative length scales, right? So here, if a tsunami is 100 kilometers, and this is 500 meters, this is a small parameter, okay? And we wanted to study numerically. Actually, some of the theory was available from acoustic waves, so we wanted to illustrate it and discover more things. So we had to do I had to do a good modeling, and then so come up also with an efficient, stable, accurate numerical method for a slightly simplified equation, because this is very complicated and very time-consuming too, because it's 2D. Okay? So let me tell the story how this went. Okay? So this is already the dimensionless equation. Okay? And I'm going to call this Laplace equation, even though it's kind of already a scaled Laplace equation, because this came out because we scaled, this is in the paper, I'm not showing you, I scaled the x variable differently from the y variable, okay? Because of the long waves and blah, blah, blah. Okay, so no way. So how am I going to deal with this problem that I actually want to put the topography not smooth like this. I want to put the topography with corners like this. See if I can get it rapidly varying, so that I can have a PDE. This is what I did in this paper. There was nothing numerical in this paper. So I could get a PDE that looked like a perturbation of this one. Because the one for the crust of the Earth, it is piecewise constant, because it's layers. Okay? And in some asymptotic theories of derivation, the former, before I did this paper, derivations of shallow water models, right? One would do expansions, as I'll show you, about the bottom. Well, but if you have corners, you don't even have a continuous function. So most of the theory that was available was not only for small amplitude bottoms and smooth bottoms, so that you could differentiate this function here, which is the profile of the bottom. And what this condition is nothing more. It's written in a way that maybe you can't recognize, but it's nothing more than the Neumann condition. So this problem, in words, starts with a simpler part that we've seen in this course, that kind of we would know how to solve, which is Laplace equation inside, Neumann on the bottom, and then the complicated part, the wave. The wave, which means I have a boundary that changes in time, and I have to put a nonlinear evolution equation there. So basically, actually, a good way to write this is like this. I have a time-varying domain, because as the wave passes by, the domain changes. Very interesting. Complicated, but in an interesting way, mathematically speaking, and so on. Okay? So the trick to do this, which I'll mention here just a little bit, and later on I'll show you computation, is this. What I did and the original idea was not mine. There was a paper by Hamilton. So I used an idea by a paper by Hamilton. Journal of Fluid Mechanics. 77, I believe. Let's put the data correct. Hamilton, yeah, 77. That he proposed to use a conformal mapping. Not for anything like so severe as this, but maybe for something like this, which also you can do conformal mapping. And what was Hamilton's idea, which also was not his, but he used from another paper, but adapted more for this problem, but his paper was didn't really give the result I wanted, so I basically worked on his paper. The idea is to do this. He took, first, think of it, take the undisturbed channel, okay, and map it. Let me actually correct this. Maybe I should do the drawing a little better. This is Hamilton's idea. Let me draw this a little bit. So Hamilton proposed this. I hope I can draw this. So Hamilton proposed to do a conformal mapping. Let me call the map F. Okay, so this is, let's call this the Z plane. Let me call this the W plane. The Z plane is X, is Z equal to X plus IY. The W plane is Xi plus I zeta. Okay? And here's the free surface. He decided to put the free surface in the middle. That's no big deal. And he reflected the fluid domain. This is omega. Okay, and he reflected the fluid domain about this region, and he mapped the fluid domain onto a strip. Okay, so this is a uniform strip. Okay, so here's a point that I've never mentioned in the fluids course or in the PDEs course, right? Some of you have seen already how to reduce this equation to the Boost-Ness equation for the flat bottom. Well, if we know how to do this for the flat bottom, right, this is good news. Because basically I know how to do this here. Right? This is the flat bottom case. Right? So this topography, right, goes, maybe let me put colors. I hope the red shows up in the video. I think it will, but this topography goes to here. Right? And I know how to reduce this equations in a flat bottom region. Right? The fact that he reflects the domain, it helps in some sense, because basically you get, when you expand about here, it helps you. I won't get into this here also. It's information I won't be able to explain you why it's good. But just think of it that it's no big deal, right? I mean, if you map this domain into that, that's what matters. This is the physical domain. This is just an image of the physical domain. Right? That helps you in the expansions because you get odd functions here, so you gain terms, blah, blah, blah. Let's not worry. But the interesting thing for us to know here is this. If I'm trying to solve Laplace's equation in here, or with this, it doesn't really matter because this rescaling, I can remove it and so on. But if I'm trying to solve Laplace's equation in here, what equation will I have to solve in here? Question for you. That question you can answer. Let me drink a little bit of water to give you 2 more seconds. Yes. So Marshall said the flow is still potential flow. Why am I solving Laplace's equation here? Because I have a flow that is incompressible and irrotational. Remember, we mentioned about these things, even though it's not a fluids course, we mentioned about these things with the interface problem, right, the Kevin Helmholtz. So if I'm solving Laplace's equation here, and as we saw also in that interface problem, right, I'm going to actually have to solve Laplace's equation in here, because the fluid in here will also have to be incompressible and rotational. And the fact that I'm doing the conformal mapping, which is sort of an analytic function, right, the conformal mapping, I don't change the analyticity of the function. So when I do the composition, it's still an analytic function. Therefore, it still satisfies Laplace's equation. So that is, in other words, Laplace's equation is invariant under conformal mapping. Okay? The only thing is that the Schwarz-Christoffel mapping, here's the name, okay, which there's a book by Driscoll and Trefethen only on that. It's in the references. I think the Schwarz-Christoffel mapping, is a mapping that's specialized for polygonal regions. Boom. But then you have to pay a price. There's theorems proving things in the book by Trafath and Driscoll. There is. But then there's one thing. What do you think happens here at the corners? Something is being kind of broken, right? So let's think in an intuitive way first, right? Of course, in the book, there's no noise, breaking anything, but this is my little sound effect. It's broken, which means conformal mapping, we preserve angles, right? So here, we're definitely not preserving angles. So it's not, the mapping has singularities. It's not conformal at these points, right? Which depends, and the singularity depends on the internal nodes. Okay, so if you look in the books or when you learn about the numerics, as I'll show you to you a little bit later on, you will see these become parameters. So at some points where the node, I think, is less than 180, these nodes you have basically it's non-conformal because the Jacobian of the transformation is 0. And here, actually, the Jacobian blows up. Okay, but no problem at first. And in particular, because as I'll show to you, I'll indicate to you, you will not see exactly all steps, I only need the Jacobian of the transformation here along the free surface. So it's an epsilon away from the singularities, which means, so in this article I show that, but I'm not going to show it to you here, and I haven't shown this in any of the courses, fluids or whatever. The Jacobian is C infinity. We're just an epsilon away, so it's okay. Okay, so this is just an information. Now, I want then to learn how to go back and forth here because I can then write my equations here because here I know how to do things as if I were in a flat bottom case. And then I come back to my original variables and actually I only need the Jacobian on the free surface, which is good news. Okay, so I'm going to sketch that for you in the following minutes, okay? Now, in this paper here, the first one, this paper here, there's nothing numerical. There's no numerical nothing, neither conformal mapping nor dynamics. It's just modeling, okay? And the conformal mapping numerical one is good then to extract numbers and so on, right? But in theory, it's okay. So what happens when you do conformal mapping of the Schwarz-Christoffel type? Okay, and actually when you do it numerically, you see this. It's very nice. So here, you're going to just get the information. So it's basically an iterative method that checks ratios. Sort of what Driscoll does and does in a beautiful way because you can do it in a very visual way, whatever, is that, but it's a sophisticated software where it's an iterative scheme to solve a nonlinear algebraic set of equations. So it's not AX equal to B. And he keeps on checking ratios and so on. And these are related, and here's some information for you from conformal mapping, related to the pre-images of the corners. So basically, let me do a caricature, okay? So I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay. So it's a caricature, okay? Okay, so this is just a caricature. I'm just putting 10 pre-images, okay? The spacing is irregular. So these are called pre-images of vertices, okay? And maybe I'll show you one formula. This I'll show you one formula, not today, but when I talk about the numerical Schwarz-Christoffel method, is that if you find the pre-images of your corners, you know the mapping. You've done everything to some extent, right? Just keep that in mind. I'll come back to this later on. But finding the pre-images is a non-trivial numerical method that is iterative and so and so. but you have that for free in MATLAB, and then produces beautiful pictures, okay? All right, so if I have this mapping, okay? So if I have this mapping, I then can do my asymptotics for these equations here and come back. So let me sketch this for you, okay? All right. So in the W plane, our system becomes this. I'm of course skipping some details, okay? But just not, but I want you to understand understand the story. I think I have it right. I think I have it right. And, okay. And let me just write like this. Let me see, where did I write this? Sorry. No, let me just do it in a simple way where. Okay, so I better write like this. It's more simple than writing. So what has happened here? Actually, let me exercise with you a little bit like interaction. If I didn't say anything, do you know? Can you see what I did? At least in words. Of course, you don't have to check calculations. Just in words. What did I do? Let me help with the first thing. Here I said, well, this is not quite Laplace's equation because I have this beta here, right? So then in my canonical plane, let me call this a canonical plane where things get simplified. It's always a flat bottom, right? So in the canonical plane, my variables is xi plus I zeta. So I rescaled zeta to zeta tilde just to remove the beta from here. Okay, that's all. So forget about it, just think. I have Laplace's equation. Now, I had Laplace's equation there too, abusing a little bit of the word Laplace's equation. Right? So I have Laplace's equation. This is the first news, right? Because we know conformal mapping doesn't change a harmonic function, right? Still a harmonic function. It's invariant. Laplace's equation, Laplace is invariant under conformal mapping. Everybody's okay with that? Okay? The other good news is this one. Let me write it like this. Trivial Neumann. Why? Because now Neumann is, yes, Eduardo.
In the z-plane equation at the bottom, the z-plane equation, shouldn't it be phi there? Or is it phi x?
Oh, here.
Yeah.
No, yeah. Yeah, I was missing this. Let me just double check, see if I'm not making a mistake.
I was thinking that if you have no topography or flat bottom topography.
No, wait a minute. I'm writing it wrong. Yeah, it should be phi y. Yeah. I see. Yeah. Wait a minute. Yeah. Because if it's a flat thing, it should be, yeah, that's right. And let me just double check if I didn't. Thank you. Yeah, I am missing here the phi x. Right? Thank you. Yeah, because it's like the gradient of phi, scalar, the normal derivative. So I got to have both. Thank you. So it was wrong. Thank you. Okay? Thank you. Okay, so this is good news. Now I have Neumann equation, Neumann condition at a flat bottom. So this very complicated equation that Eduardo just helped fix here, this very complicated equation is simplified. Note that if this function here, if h is not smooth, right? I can't even make a proper meaning in the classical way of this guy. And also in the Hamilton paper that I mentioned, he shows that if you try to do an expansion to simplify this equation, and this gamma here is an epsilon, every time you differentiate this guy, you get a 1 over epsilon coming out. And if you have a 1 over epsilon on something that you're doing a power of epsilon kind of expansion, like we did in another case, this is going to mess up our power expansion because you want high order terms to be smaller and smaller, but high order derivatives produces 1 over epsilon terms. So that generates a mess of reordering of the series that is an indication that I'm doing something wrong. Right? Calls attention, I'm starting to mix up the order of the formal series, and that is bad news. We have to stop and think why that's happening. So can you more or less understand what I'm saying? Because it's a 1 over epsilon. If I differentiate, okay, it messes up things. Okay, and now the only thing that happened here, the only two things that happened here are this. This is the Jacobian of the change of variables, which is basically the Jacobian. I can write it like this. Using Cauchy-Riemann. Can you see why? Let's do it without me writing on the board. The Jacobian of a change of variables is going to be, so I'm going to write here on the wind, right? It's like corridor. The Jacobian of a change of variables is going to be dx dxc, dx d zeta, dy dxc, dy d zeta. Let's forget about the tilde, okay? So it's dx dxc, dx dxc, dx d zeta, dy dxc, dy d zeta. But using Cauchy-Riemann, dx dxc is the same thing as dy d zeta. And dx d zeta is minus blah, blah. So we can write it like this. Okay? So this is the Jacobian. Okay? And actually, the Jacobian at the free surface, zeta equal to 0, and this is a little bit of the nice thing of the trick of Hamilton. Here's the first thing. This is just dy d zeta squared. Why? Because of the symmetry here. Here, dy does not see, y is not changing here, right? It's not changing here, y. So dy dx is 0. Okay? Okay. What else I want to say? And then we're going to call this in the next equation. So we're just going to give this a name, which is our metric coefficient. So it varies only in xi. This is called our and believe me, here you have just to believe me, okay? Because it's not obvious to see, right? All these steps. And this m of xi, I'm just giving a name to this guy since it's evaluated at y equal to 0. So it only depends on xi. So the Jacobian only depends on xi. And I'm going to give it a name, m squared of xi. Why am I putting the square? Because of this square, and because the only guy that's going to appear in the next equation is the m of xi. Okay? So please, don't feel bad if you're not understanding all the steps, because I'm skipping many steps. But I want to give you the flavor of the modeling, the mathematical modeling, using conformal mapping, and then I'll show it to you later on that actually the conformal mapping can be done numerically, and that we're going to get an equation better for computations. Okay? So this is now going to be the next step. Okay, so now, right. Okay, so now here I'm writing, using expansion that has been seen in other courses, okay, which is this. So this part I'm going to skip. I'm just going to write it down, but those who have seen it will recognize it. Those who have not, no worries. You'll probably take the PDEs course or the fluids course, or you can check it on the web. So this is an expansion. Those of you who did PDEs and applications or fluids, do you remember something like this? Right, which is the potential. This is an expansion of the potential. Expansion about the flat bottom. Okay, so in the course, we saw it over the physical flat bottom, okay? So it's an expansion in the depth. So powers of the depth, okay? So in the other courses, both fluid stuff, this was x and y. But here, because of the conformal mapping, it's in C and zeta because I'm doing the expansion here, pretending I am in the flat bottom case, because that's my canonical domain. But then after I do the expansion, I have to come back, somehow connect, not necessarily come back, but connect to the physical domain, okay? So this, how to get this expansion here, we've seen this for sure in the PDEs and applications course that some of you will do in the future. Some of you have done, okay? And I'm not so sure how much we've seen this. I think we saw this also in the fluids course, for those of you who did the fluids course, right? In X and Y, okay? So this leads, this expansion, this leads to the Boussinesq system that I will write right now. Well, let me actually write this a little better. This leads like this to the terrain. That's the title of the paper, right? To the terrain following. I will explain this in just a second. To the terrain following Boussinesq system This is a system along the undisturbed free surface. And this is called a weakly nonlinear, weakly dispersive, because alpha is order epsilon. Oops, handwriting getting tired. And beta is also order epsilon. Okay, so this is called the weakly nonlinear, weakly dispersive system, which is written in the canonical variables. And excuse me, let me highlight here where the Jacobian is appearing. M, M, M. Okay, let me now highlight where the parameters appear. Alpha, weakly nonlinear, alpha, and here the dispersion parameter, beta. Okay, and let's double check here a few things. Okay. So if beta is equal to 0, okay, we get a hyperbolic shallow water system which is this, but variable coefficient, okay, which is the m. Okay, if m is identically equal to 1, which means the Jacobian is 1, which means there was basically no change of variables, right? M, so this means flat bottom we get the equation we had before, like we saw before. And if we make alpha equal to 0, so look, if we put alpha equal to beta equal to 0, m identically 1, look what we get. We get eta t plus u of c equal to 0, u of t plus eta c equal to 0. This is an equation we already saw. It's like the hyperbolic two-way wave equation. Right? The only thing that's written in C, we saw it in X before. This guy, this guy, this guy, this guy. Okay? Is it clear? Please ask questions. I see some of you, you look like you're thinking. Some of the things, I am not being fair because I'm skipping some points that maybe we've seen in other courses. And actually, there's some points with like the conformal mapping you have never seen before. But I know that from what you have seen in the PDEs course, in the fluids course, you should have an idea of what's going on. So if there's any doubts, ask, because then it's my problem. I'm not communicating well. Okay? So this is a simplification. So this is our reduced model. Which is 1D. 1D. So we started with a 2D problem, and we have a 1D problem. So where have I mathematically put the information of the vertical structure of the problem? The information of the vertical structure of the problem comes in two flavors. Flavor 1, which is geometrical. Flavor 2, dynamical, right? Because the problem that was 2D, it has the two-dimensionality of the problem comes from two aspects. The geometrical one, topography, blah, 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 and the dynamic one, what is the fluid doing in the dynamics. The geometrical information came in an approximate way through the Jacobian, which is m. That's where the information, if I had no waves, look, if I had no waves, the geometrical information from mapping this to that is the change of variables. It's in the Jacobian, which is dx dx, dx d zeta, use Cauchy-Riemann, and evaluate it at the undisturbed level. It is actually exactly the m, right? It's here. So this is how I have put mathematically the geometrical information into a coefficient rather than into a boundary, right? So the geometrical information was first on the boundary, so it was in a geometrical way, and now I have put the geometrical information in an algebraic way inside a coefficient, right? So this is here. No, not here, here. And the vertical structure of the dynamics was approximated here. And the fact that I took only the first two terms of this expansion, right, because I only have one power of beta, not other powers of beta. Just think of this as epsilon. So I'm taking only the order epsilon guys here, not order epsilon squared, right? And then the vertical structure of the dynamics as a first order approximation comes from here. First order in alpha, first order in beta. Right? And that's how I collapse and approximate my dynamics up to here, only on the free surface, only over the blue line. So I have mathematically reduced my 2D problem to a 1D problem, which was nice mathematically as an exercise, and as a research result, because I did this for rapidly varying non-smooth topography. So that gave me a very important paper, actually one of the most important papers in my career, because out of this, many things came. Then came my first PhD student, which I'll talk next time, which is Juan Carlos' thesis, and etc. What? So this was an important paper, satisfaction, plus it generated other papers. Okay? And why? Because then I had this equation here, to present, say, to Juan Carlos Munoz, student was from back in Colombia now, Cali, and say, look, Juan Carlos, now let's try to, using this equation, let's find a good numerical method and try to study the interaction of waves, long waves, which is a pulse-shaped waves. Actually, this system has solitary waves. Let's study solitary waves over rapidly varying periodic and random bottoms. Why did I want to do random bottoms? Because there was a theory by Papanicolaou and collaborators, okay, which had very interesting results. And we wanted to then check the results, if we could at least computationally, and maybe who knows theoretically, and Juan Carlos did both theory and computations, to generalize Papanicolaou's theory for a more general model. And what was then Juan Carlos' his theory, which is the second paper I'll speak, but on next class. What did he do? Well, we did, okay, since nobody understood this problem, right, it was new, right, people understood the linear hyperbolic one. The hyperbolic one is basically linear hyperbolic, it's alpha equal to 0, beta equal to 0, but with a variable coefficient here. That's the one of the crust of the Earth, okay? So with Juan Carlos, I said, well, let's do the first generalization. Let's do the first generalization of what the acoustic people did, because we knew they had some theorems and stuff like that for acoustic waves in random media. And one of the theorems, for example, was that there was an apparent diffusion. That is, if I put this equation here for the acoustic ones, the equation is like this. There's a z here, there's a z here, there's a 1 over kappa here, I think z, and there's a rho somewhere, I think here. If these guys are random, this equation has, for the right-going wave, the wave going down the crust of the Earth, it looks like it's under the effect of diffusion, even though there's no diffusion coefficient here. So it's really non-intuitive. I'll try to pass to you on the intuition I've acquired from the mathematics. So it's really nice. I love having a physical intuition, but I did not have a physical intuition. I could look at the problem forever. I don't think I would have the physical intuition, but the math gave me physical intuition. And I want to share that to you without getting into all the details. And the numerics was then to see if what happened with acoustic waves was also happening with water waves, and this was the first then new mathematical ingredient, which was basically one of the main things in Juan Carlos' thesis, that he could do the theory and the numerics, is that we kept the dispersion, but we did the linear problem. Okay, so if we do this, oh, the eraser is far, yeah, but I have time to, in 15 minutes I can get the eraser, which is so I can write this a little better. So in Juan Carlos' thesis, we looked at the following problem. And I'll tell you how the numerics were done next class, okay? Okay, and now I put here, say epsilon, just to call attention. So this is a dispersive perturbation of a hyperbolic problem that looks like the acoustic problem, right? The coefficients are a little bit in different places, but it's okay. Okay, so yeah, this is okay. So Juan Carlos was able to do some theory for this, actually following a paper by these two authors, Berliand and Burge, a paper in the journal called Wave Motion. '94, where they had done some theory for the hyperbolic problem, right? Showing the apparent diffusion and so on in a deterministic way, in a nice way, easier to understand. So it was very interesting for me. Let me share the story with you that it was my first student doing a PhD. I had these ideas, and I said, I think we can do it, Juan Carlos. And I was asking him to check if some of my ideas were correct. Maybe I had done a mistake. And then I was at a meeting in Stanford mostly of acoustic waves organized by Papanicolaou, where Robert Burge was there, was a collaborator of my advisor, George Papanicolaou, and a very nice guy. And I asked Bob Burge, look, I've been reading your paper with a student of Berlin, your paper with Berlin and so on, and we're having these ideas of maybe how to do the same problem but with dispersion. I mean, is it clear to you? I mean, do you have this, have you done this, whatever? And it's very nice that you see somebody experience and say, I'm not sure if it works or whatever. Which means that's good news. I mean, maybe he could give me some valuable information, but if a person like him stops a little bit and thinks, I'm not sure if it can be done, how it will be done. So that's good news. So we chatted a little bit and said, yeah, go try it, right? So I came in with Juan Carlos. So we did this. We did the theory, which I will not report to you. Sometimes I give it as a reading exercise in the PDEs and application courses, because you basically have to rewrite this equation as right and left Riemann invariants. So you have right and left modes, blah, blah, blah. You do some manipulation. And at the end, you can show that actually the right going mode, the one that interacts with the topography, is under an apparent diffusion. I will tell you at least next class what does apparent diffusion mean. Okay? I'm not going to tell you how you get there, but I'm going to tell you how I mean, so that you can understand. Why am I going to tell you? Because it's interesting, also so that you can understand the numerical simulations with this equation, which was in Juan Carlos' thesis. And we had to make sure that because we wanted to check this very subtle numerical diffusion, not numerical diffusion, this very subtle apparent diffusion due to the random topography, we had to make sure the method had no numerical diffusion, or else which diffusion are we looking at? And we succeeded. I mean, Juan Carlos was doing the competition, succeeded. So next class, I'll show you that. And then, after we understood this, there's another paper with Juan Carlos and with Jocelyn Garnier, where then we studied really solitary waves, because then we put the nonlinearity, okay? And we kept on doing things in that. Okay? But one interesting thing, well, I'll tell you next class how we did the numerics for this guy, right? And this term here that C has a crossed spatial derivative with time derivative. It's not obvious how to solve this linear system, right? At first, let me sort of just make a little bit some provocations for next class. Look, I could write this like this. Just put the 1 over m here. I could write this like this. Why am I writing it like this? So it looks like an OD, so I can do the method of lines. But this guy, he gives me a headache because I have time here and here. How do I solve this numerically? I won't answer it today, so I make sure you come next class. I know you're going to come next class anyway. But even if I still, let's keep the suspense for next class. So how do I solve this? Okay. And then let me tell you a little bit. Let me tell you two things because I have time. One thing I should have said, and I forgot. Let me use this space here. Why is this paper? Okay, here. Why do I call this the terrain following Boussinesq system? This is important to say this class because I'm presenting this idea. Why is this called the terrain following Boussinesq system? So this word, this term, I got it borrowed from atmospheric flows. At the time, we had here a project in IMPA that was dealing with the CPTEC, which is our Center of Weather Prediction in Brazil, and so on. and I had learned some things. And the idea is like this. So let me do a drawing here. Let me do a smooth topography, okay? So in atmospheric flows, right, in atmospheric flows, here on top of a mountain, say, you have sort of the atmospheric pressure and so on. And they use sometimes the atmospheric pressure that as you go up goes down, right? As we go up in the atmosphere, it goes down. Sometimes they use the atmospheric pressure as sort of a coordinate system, okay? So, and then they call it a terrain following, because it sort of follows the terrain to some extent. Here, I'm using it for another reason, even though I like the terminology, but still I can call it terrain following. Why? Let me do a drawing here by hand. In next class, maybe I'll show you the computational version of this drawing by hand done by the Schwarz-Christoffel toolbox, which draws beautiful pictures. It's like this. Okay, let me draw like this. This is, here in yellow, I have my XY coordinate system. But in white, I have my Xi zeta coordinate system. Because when I map this to a flat bottom, so this is in the W plane. This is in the Z plane. Okay, so in the W plane, my coordinate system, Xi zeta, is Cartesian. Okay? So, right, and these are all right angles. It's a Cartesian coordinate. Xi, this is Xi zeta. But then when I do conformal mapping, as I said, preserves angles. We learned this in complex variables. So this means that all these angles here are right angles because they're right angles here. It preserves angles. Okay? So the nice thing, another nice way of thinking about conformal mapping, okay? If you don't like, and sometimes I write it like this because I think it's very appealing. If you don't like thinking that you go to a computational domain, which is the canonical domain, if you don't like thinking about that, oh, I don't like thinking that I go to a computational domain, you may think of conformal mapping as producing, and I use this in other problems, in particular problems that Christian is studying, which is branching channels, right? The operator is not invariant anymore, but I use conformal mapping, and I want to mention this more towards the end of this course, as a boundary fitted coordinate system. You know what boundary fitted means, right? It fits exactly on the boundary. So the boundary is a level curve of your coordinate system. So here, look, my boundary is a level curve, zeta equals to something. It's like a potential isoline of the coordinate system. My free surface is another level line. Okay, and this line here, what is this line here? This line here is zeta equal to a constant. It's like, it's one of these lines. This line here is Xi equal to a constant, one of these lines. You agree with me? So therefore, the conformal mapping as a change of variables and as a boundary fitted change of variables, because it fits the boundary perfectly, right? If I don't want to think of this as the computational domain, as the canonical domain, right? It is a computational domain, and there's other problems with this too. You can think of the conformal mapping giving me another coordinate system, a curvilinear orthogonal coordinate system which preserves the Laplacian. That's another way of saying exactly what I've been doing. Do you agree? It's a curvilinear coordinate system, orthogonal coordinate system, that preserves the Laplacian. So in this physical domain, I have Laplace's equation here, whether I do it in xy or if I do it in xi zeta. Okay? So cool. So this is one thing I want. So this is why the name of the model, I decided to use the name of the model, terrain following coordinate system, or terrain following Boussinesq system, because it's a Boussinesq system written in coordinates that follow the terrain. And the fact that it works well is because actually when I talk about horizontal speeds, they're not quite horizontal speeds. When I do these expansions here, they're not quite horizontal speeds. They're terrain following speeds because it speeds in this direction here. They're tangent to the terrain following. And actually, the asymptotic expansion, this approximation here, this is what this u is a terrain following speed. I didn't mention anything. It's actually an average one, but forget about it for the time being. But this is related to terrain following speeds, which is different from a horizontal speed. Okay? And note here, this is my last comment because time is almost over, is that a horizontal speed here is highly variable because it can be very large here. And what is the value here of the horizontal speed? 0. So you see, that's like an intuition why the asymptotic expansions with the terrain following guys is better than the Cartesian one for this topography. Because the Cartesian one, things change abruptly. And for the terrain following one, not. Because as you will see in graphs, if I have a terrain following just one step like this, the curves are kind of like this. And the terrain following velocity is kind of something like this. So you see, it's much better to average over these speeds, which are non-zero, than the one that's 0, then poof, fast. Okay? And these pictures here, actually I'm not drawing that bad today. It's not so bad. They're beautiful if you do it in the Schwarzkopf toolbox. We'll see this next class. Okay? So today there was nothing kind of numerical, but it was something which is really a very, very interesting part of the job, I think, of an applied mathematician and so on, is like understanding the PDEs, understanding to prepare the model, and without cutting it too much, right? Without sacrificing too much, but like it's like getting a stone and sort of making it simpler and more beautiful so that you can use it. Use it for what? For theory, if possible. In that case, Juan Carlos was able to do some theory. Not always you can. But sometimes you can infer some things from the theory. And doing accurate numerics to reveal information from what? Well, in my case, I want to reveal as much information as I can from what? From both the math, the PDE aspect of a problem, and the legitimate, true physical aspect of the problem. I'm not just doing this for technical reasons, mathematical reasons, which is fine. Some people do that, right? That's fine. It's good that we have different tastes and we can populate mathematics as the best possible. But here the problems are very complicated, and those are the ingredients. Okay? So we finish here and come back on Thursday. And I'll send you copies of this article so you can follow.